Alright, this is the lesson 4.2 supplement for those of you in the BC class. Those of you in the AB class, this is a continuation of actually the 6.4 supplement. This is investigation number 2 for you. So let's use this graph again, y equals 2t. That's this line. I drew it out for you this time. Say thank you. And I want you to evaluate this integral. The only difference now is I'm actually not starting at 0, but I'm starting at 3. So notice that my area is no longer a triangle, but it's actually this lovely trapezoid. Or you can think of it as a larger triangle subtracting a smaller triangle. Okay? So notice that x is still my variable. It's the one that with the upper limit. And so that's why the integral is a function of x. This time I'm calling this g. And what I'd like you to do is let's see if you can evaluate the integral using the difference in areas of two triangles at different values of x. So the first one I have here is really 5, so I'm really asking you to do this. What is the integral of 3 to 5 of 2t dt? So imagine this was 5, then you'd have to calculate. Now, can you see how there's like a big triangle? I'm going to draw this out here. Big triangle minus the smaller green triangle, right? And that's how I'll find my answer. The large triangle has a base of 5, right? If I'm going right to 0. And then the height, of course, is 10. So really that's 5 times 10 divided by 2. And then the smaller triangle here, the base is 3. I think the height is 6. So 3 times 6 divided by 2. 5 times 10 is 50. Divided by 2 is 25. So this is actually 25 minus 9, which I think is 16. Okay? Now, you do the next one, please. Okay, and you don't have to draw that picture again. I did that for you. You can just put this information in the box. Eight times the height, which is 16 divided by 2. We're subtracting that same little green triangle, so same 3 times 6 over 2. That'd be what, 64 minus 9. I got 55. Now, let's do this in general now. So if you think about in general, from 3 to x, this is for anything x. Remember that big triangle that I had here? I'm going to draw it again this time for you. The base would be x. The height then would be, it's given by that equation, 2t, so 2x. And then we're still going to subtract off of that small triangle. And that small triangle is always the same, 3, 6. So if you're looking at this expression, it would be x times 2x divided by 2 minus the same 3 times 6 over 2. And I hope you'll see that this time I get x squared minus 9. Okay? And so ultimately now, what happens if I'm asking you to calculate the integral g of x, which of course is the area underneath the curve of 2t, starting from x equals to 3 and ending at x equals to x, using that particular rule. Well, what we found was that this g of x function is just equal to x squared minus 9. And the question I have for you is, what do you notice about that number you keep subtracting? That 9, yeah, it is the same. So 9 is a constant, okay? And it represents what? Is a constant representing, okay, the area of the small triangle, right? That one in green. I'll draw a little picture. That one in green. Okay. That we are always subtracting. That we are always subtracting. Okay. Why? Why do we want to do that? Because of course we don't want to include that in the area. We don't want to include it. Okay. So where does the 9 come from, if you think about it? Well, the 9 is connected to this value of 3, hopefully you can see. 9, of course, comes from plugging in 3 into the x squared term, right? In the previous supplement, or for those in the AB class, that number here was 0. So if we plugged in 0 squared, that's still 0. We're not subtracting anything. It's at 0. But now we're plugging in 3. 3 squared is 9. We have to subtract that area of 9. And so this then helps us come up with a theorem. If both the upper and lower limits of integrations are constants, okay, so now it's not just 0 to x, it's now a to b, then the integral from a to b of little f of t dt is actually equal to capital F. Yeah. And notice that it's the x squared term, so really we just found the upper limit squared, or we'll say the antiderivative, and you evaluated it at the upper limit. So this is the antiderivative, because the antiderivative of 2t was x squared. Antiderivative evaluated at upper limit. But we always had to subtract off that small rectangle, or that, small triangle, which happened to be 3 squared. In this case, 3 would have been the lower limit plugged into the antiderivative, so f of a. So this is once again just the antiderivative evaluated at the lower limit. Okay. Some textbooks prefer to write it this way, capital F of x with a bar, and then some of them will just say BA like this. Others will also be more specific, f of x like this, and say x equals to b and x equals to a. All three notations mean the same thing, but I do want you to know and be able to understand that they all are the same. Okay? So once again, if you're an AB student, you're done for your notes, but if you're a BC student, if you turn to the back page, I gave you a quick proof, and so the BC students, yes, follow along. The AB students, if you want to shut this down now, that's fine, but if you want some enrichment, by all means, yeah, do this. So how do I prove what we just did there? So this time I'm going to say capital A of x. That represents the area of the region bounded by the curve and the x-axis from x equals to a and x equals x. So once again, I'll draw a picture for you. Here's a, here's x. This shaded region here is a of x. Okay? Now, if I were to plug in a for the value of x, that means my diagram really just this, from A to A. But if you're thinking from A to A, there actually is no area because A is the same value. So if you think about this, it's really just nothing. So there's really nothing, no area underneath the graph. Okay? So that's a statement that I hope we all can agree on. Now, if we introduce capital F of x as the antiderivative of little f of x, we should be able to say that the area, so a of x, is equal to capital F of x plus c. And you're like, where did this c come from? You're right. Well, this c should be some sort of constant that helps ensure that when I plug in a for little x, that area must be 0, because that's this statement here. So in order to do that, let's actually substitute x equals to a. So I'm going to take this statement now, I'm going to substitute x into, or a into x. So a of little a equals to f of a plus c. Okay. Now, let me try to solve for c. So if I solve for c, I can move the capital F of a to the left side. And remember how we said here that a of a is equal to 0. So I'm just going to replace that now with 0. So 0 minus f of a equals to c, or therefore c equals to negative f of a. Okay? Now, if I could ask you now to actually substitute this back into our equation, a of x equals to f of x plus c. Notice now what we have is, I'll use green, a of x equals to f of x minus f of a. Okay? And ultimately here I'll say note, if I replace x with now b, you'll get the area of b, which is really the, and once again this is the area under the curve, right? From x equal a to x equal to b. That's what this a of b represents here. Okay. What is the result? Well, now it's not f of x, but f of b minus f of a. Ta-da! And there's your proof. So the integral from a to b of little f of x dx is equal to the antiderivative evaluated at the upper limit minus the antiderivative evaluated at the lower limit. Okay? Important. Box this. Memorize this. Okay? All right. Just a note, because we subtract f of a from f of b when we calculate the definite integral. Oh, by the way, this is called the definite integral. A definite integral is one where the lower and upper limits are constants. Okay? We generally use an antiderivative f of x with a constant equals 0 in its formula. Okay? We'll talk about more why we don't need that plus c thing and why it's equal to 0 later on when we actually do some of these definite integral calculations. Okay? Basically, we choose a non-zero constant, but if we do that, it creates more work. And who wants to do more work, right? Especially when things just cancel out in the end. All right, but I'll show you that later on in the other videos. That's it for now.